Okay, so hello everyone. So it's not good morning and good afternoon. So it's noon here in New York City. So it's my great pleasure to have François Charton. So François is based in Paris. He's a senior researcher at Meta and Meta AI. And so he's a great scientist. Has done really a lot of interesting research in AI. In particular, recently he gave some lectures, a lecture at the Collège de France. It's a prestigious academic institution in Paris around AI and mathematics. And so his lecture was in French, so I didn't speak French, but I thought that maybe it'd be good to have a version of this lecture in English, so that the American international audience could share his insights. So let you you want to introduce yourself a bit more about your work or how you came up to work on this, and the floor is yours, François.
Well, thank you very much. Can you see my screen?
Yes. Yeah.
Okay, so I'm François Charton. I work in Meta, and I'm going to present my research topic, which is AI for mathematics. So the question we're going to study is whether artificial intelligence can model maths and mathematical language. So as many presentations these days, I'm starting with ChatGPT. Everyone does that. So this is a dialogue with ChatGPT as of yesterday, because they apparently changed everything. So I asked ChatGPT whether you could store 7 red balls and 2 blue balls into a tube that can contain 8 balls. And the first answer of ChatGPT was, of course, you just put all of them, the 9 balls, into the 8-ball tube and everything will be fine. So ChatGPT is wrong on that. The fun thing is that if you repeat the experiment several times, after a few times, you can end up having the right answer. So ChatGPT will say, oh no, of course, you have 9 balls and that exceeds the capacity of the tube. And if you insist a little more, you can get into very creative answers like this one. So we'll read it together because I think it's very fun. So I'm asking, can you store 6 red balls and 3 blue balls into a tube that can contain 7 balls? So answer should be no, of course. So the answer is yes, you can store 6 red balls and 3 blue balls in that tube, in a tube that contains 7 balls. To do so, you place the 6 red balls and the 3 blue balls, making a total of 9 balls in the tube. This is correct, note. Since the tube can only hold 7 balls, one of the balls would need to be removed. This is wrong, it should be 2. If you remove a red ball, you would be left with 6 red balls and 2 blue balls. This is wrong again, it would be 5 red balls and 3 blue balls, which would fit within the capacity of the tube, which is totally wrong. So you can see, if you ask ChatGPT on a fairly simple problem, you basically have to sum 2 numbers, forget about the colors, and compare to the size of the tube. You get right or wrong or totally weird answers. And this is sort of the situation. So I'm not saying that it's impossible, but it's not that easy to do mathematics on using a large language model, state-of-the-art large language model right now. So I'm sorry. So my subject, so this introduced my subject. My subject is using language models for mathematics. So the starting point of this was a reflection a couple of years ago about language models. So language models, we know they can process natural language. They do it very well. They're used everywhere to translate, sometimes even without a dictionary from one language to another. They're used in chatbots like ChatGPT. They can answer very precise questions, from Wikipedia, like the Galactica thing that Facebook posted a while ago. And they're interesting because they learn from examples only. So you don't need to train them, to teach them, for instance, in language, grammar, linguistic, and all that. You don't need dictionaries. You don't need translation corpora. The only thing you need is a lot of examples. That's a real lot. For ChatGPT, they're speaking about 500 billion tokens. So that's really a lot. So the question was, could they do math? And there are reasons why it might happen. First thing, mathematics is very close to a language. Second, we said we need examples, but examples in mathematics are easy. You can generate them. And third, since their apparition, transformers have been tried on many problems and they always succeed. We tried them for text, for speech, for image, and they work, and they're state of the art. So why not math? But there are reasons to doubt, on the other hand. First, neural nets, we have tried for many years to apply neural nets to math, and they fail on very easy tasks. We've seen the balls problem with ChatGPT, but integer multiplication, for instance, is very, very difficult to perform or to train on the neural nets. Also, if we think on how we humans learn math, we don't learn math from examples. I mean, no one learns multiplication in little school by looking at, many examples of multiplication. You learn rules, you learn algorithms, you learn tables. And this is even truer for advanced problems. So the idea that you could solve advanced problem of mathematics without the help of rules and theory, just from examples, is, well, at best counterintuitive. Nevertheless, what I want to do is this. I want to consider my math problem solving as a language task, a translation task. So I want to train transformers on generated sets of problems and solutions. And I want basically to translate problems, which are mathematical sentences, which like natural language sentences, into their solutions, other sentences. So I would like to ask my transformer, something like the sentence 7 plus 9, and have it reply 16. I would like the transformer to translate cos 2x into 2 cos square x minus 1, for instance. I would like the transformer to be given a polynomial at the one at the bottom, a square minus x minus 1, and get the roots as the translation of this. So train transformer to translate math. So over time, this has been the subject of several papers. So we started in 2019. So I'm going to discuss these 4 papers. There are a few others. I put them there, and you can have a look if you're interested. So before I start, I'd like to clarify something. So people sometimes ask, why? Why do you want to do AI for math? Because we already have mathematicians. We already have lots of tools, numerical tools, computer tools that do math. So why? So there's a first fairly vain reason, which is it's a challenge. It's like Go, it's like chess. It's the kind of thing people say, okay, when computers can do this, they will be intelligent. Of course, it won't be the case like Go, like chess, but it's still interesting to try to solve those hard problems. And like Go, like chess, it might teach us a few things on the way. We might learn a few things about AI, about transformers. For instance, I'm quite interested in understanding why a bright tool, because it's a bright tool like ChatGPT, struggles with my silly blue and red ball problem. I mean, why is it that such an easy problem is so hard for such a bright system? A more important reason of doing AI for math is that it's a good basis for AI for science. Science is full of math. If your AI cannot do math, it won't do science. So you need AI for math as a proof of concept if you want AI to be used in science, in research and all that. And finally, there's a couple of practical applications. So cryptography is one. We're trying to publish paper these days on cryptanalysis of post-quantum cryptography using transformers. So there are practical applications. There are direct application in theoretical physics, which basically is mostly math. So yeah. So here are for the reasons. So having said that, so what's my plan? So the plan is to use transformer to do math, and I need to do 3 things. I need to represent my problems and my solution as sequences, because it's a language model. Everything must be like sequences of words. Then I will need to generate very large sets of problems and solutions. And finally, I will need to train my transformers to train problems, to translate the problems into solutions. So first thing, transforming math into language. So it's relatively easy because a lot of the mathematics as we know it is already, words and tokens. Basically, symbols, variables are exactly like the tokens we use in transformers. So, sine, cosine, the variable, pi, gamma, every Greek letters we use, this works the same. Also, a lot of mathematical objects are already sequences. A vector is a sequence of digits, of numbers. Matrices are sequences of rows, which themselves are sequences of numbers. A graph can be thought of as a sequence of edges, which are themselves pairs, so sequences of nodes, which could be ordered or not, depending on whether you want a directed graph or not. There are basically 2 issues there, representing numbers and representing expressions like functions, equations. How do you put them into sequences? So for the numbers, you can note that integers are already represented as sequences. That's the way we write integers. And integers is just a sequence of digits preceded by a sign. So you could decide to represent, for instance, the number 1024 as plus 1024 in base 10, 5 digits. And that's a sequence. And that works. If you think this sequence is too long, then go for base 100, and then it's plus 1020. You've got 3 tokens, and it works as well. So integers are easy to represent, and if you have integers, of course, you have rationals. Real numbers are slightly more complicated. So some real numbers are already tokens. You know, when you say pi, or when you write square root 3 plus 2, it's a sequence of tokens. It's basic. But most of the real numbers, you cannot represent them as digits because there's an infinity of them. So you would encode them like you do in computers, so like floating point numbers. So I usually use base 10. You could use other bases, of course. And you can represent a number as 3 parts, a sign, a mantissa, and an exponent, which can be represented as 3 or more tokens. And of course, if you have reals, then complex numbers are pairs of real, etc., etc., etc. So you can see that numbers are not really a problem. The next point is to represent expressions. So how do you represent an expression as a sequence? So I use a very old technique. You know, it dates from last century, 1930, I think, in logic. It's been used in computer science, saying that expression can be represented as trees. So for instance, the expression 2 plus 3 times 5 plus 2 can be represented as a left tree on this slide, where you have all the operators, plus, times, that correspond to the internal nodes of the trees, and where the leaves are the digits 2, 3, 5, 2. And if you are a bit creative about, you know, your vocabulary, you can add variable like x. You can have new function like the power or the cosine. And so the function that is in the middle there, 3x squared plus cos 2x minus 1, can be easily represented as yet another tree, not much complicated than the previous one. And if you want to be even more complicated, you can add Greek letters representing function, more variables, and derivatives, you know, which are binary operators. They're just operators. And you could define a partial differential equation like the one-dimensional wave function on the right is still a tree. So what I'm saying here is that a lot of expression, most mathematical expression, can somehow be represented as trees. And what's nice is that once you have a tree, it's fairly easy to get a sequence because you can enumerate the tree in a specific order. So we use Polish notation, known in computer science as pre-order enumeration. So basically, you start from the roots, you enumerate the parent before the child, and you read the children from left to right. So here, you know, start from the root, parent, so plus, left child, it's 2, right child, so start from the root, times, left 3 plus 5, 2. And you see, I'm ready for the transformer now. All my expression could be transformed into trees and now in sequences that can be read into the transformers. So the first part of the job is done, if you like. The next order of business is generating data. So we'll see several cases later, but there are 2 basic approaches. The forward approach, which is a naive approach to generating data sets. So you generate a random problem, P, and then you need to compute a solution to this problem. You have a pair, problem solution, and you add it to your data set. And you repeat this millions of times, and you have your training and test data sets.
Can I ask you, does it apply also to random variables, like some variable that follows a normal distribution, for instance? Would it work?
Yes, you could generate. So for a random number, you would probably not use this. You would just generate random numbers. But you still need problems and solutions.
Yes. Yeah.
Okay. So the idea is that the problem with the forward approach is that you're going to need an external solver because you need to compute the solution for the problem. So this is limited to only the problems you can solve or the instances of problem you can solve. Okay. So it has its limits. So most of the time we're using a backward method, which might seem counterintuitive, but you will see it works very well. Instead of finding the solution to a problem, you can find the problem to a solution. So you generate a random solution. Mm-hmm. And in many times, you can derive the problem from the solution, and then you get a pair and rinse, repeat, and there you are. Okay. So what do I mean when I said generating random problems and solution? You know, what's a random problem first? So the thing not to do is to try to work on the problem space and define a probability distribution on the problem space. This is very hard for most problems. What's a random function? Well, good luck with that. So we're going to leverage tree representation. Basically say one problem is one expression, is one tree. So instead of generating a random problem, I could generate a random tree. And then once I have a random tree, I could populate it or decorate it, if you like, by generating randomly problem-dependent operators for the internal nodes, and then randomly selecting variables, symbols, numbers for the leaves. I get a tree, which I can enumerate to get a random expression. So I have this way my random problem. Okay, so this is how you generate problems and solution. And finally, we're going to train models. So I'm not going to lecture you on transformers. You've probably heard of them. I'm using sequence-to-sequence transformers. So basically two-stack transformers where you have an encoder, which takes care of the input, the problem in my case, and a decoder, which decodes the output, the solution, token by token. So it's an autoregressive decoder. We train the model on generated data. It's supervised learning. And we minimize cross-entropy. So we treat the problem, the decoding problem, as a multi-class classification problem, the thing for which you use cross-entropy, which means that it's a pure language task. The model doesn't care, doesn't know about the math. It's only, language for it. It's a word game, if you like. At test time, so you test on held out data, on data that has not been seen at training. But there you do math. So you need an external tool. So all the problems need to have an external verifier. That's a limitation of the approach. And you use this external tool to check that the solution is correct. And there you can use mathematics. So you do mathematics at test time, but not at train time. Finally, we sometimes use a trick called beam search. Beam search, we leverage the idea that the transformer can generate not one, but several solutions because you predict the next token. So instead of predicting the next most likely token, you could predict the next 5 or 20 or 15 next tokens. And since you have a verifier, this provides a model with several guesses. So it can provide several guesses of the solution, and having the several guesses, you can check. So it's a way to improve model capacity. So this is for the sort of introduction to what I'm going to do. And now I'm going to present you some results. So the first thing I want to present is deep learning for symbolic mathematics. This was our first paper with Guillaume Lample in 2019, and so 3 years ago. We studied two problems of symbolic mathematics. So symbolic integration, so you have a function, you want to find the antiderivative of it, and ordinary differential equation, which is a glorified version of the previous one. Basically, you have a relation between a function, one variable function, and its derivative, and you want to find a solution to this. So why these problems? First, because they're interesting. They're advanced problems. They're taught at usually undergraduate level. They're non-trivial. Mathematicians will not solve them in their heads. You need paper, and sometimes they're quite hard. They're also hard for machines. There are algorithms for integration, none I know from ODE, but they're very hard to implement. The Risch algorithm is never fully implemented even in Wolfram Alpha or state-of-the-art tools. And also they involve pattern recognition. When you want to integrate a function, if you have trig in the problem, you'll have trigs in the solution. If you see 1 on X, you'll get a log at the end. So there's a lot of pattern recognition. That's how we humans solve it. And pattern recognition is something neural nets tend to be good at. So it was a way to simplify. It was the kind of problem we thought neural nets had a chance to solve. So to do that, we needed to generate data. It's always the same. So the forward technique, you generate a function, the function to integrate, so small f of x, and you need to compute the integral. So you use SymPy or an equivalent tool, and this is very slow, and you're limited to what SymPy can integrate. The backward approach, and it's a good example here, instead of generating the small f, you're generating the solution, big F. And then computing the problem is very easy. The only thing you need to do is to compute the derivative, which is very simple. It's a set of rules. You can program that in a few lines of code. We use a third method, which is called integration by parts, which looks a lot like backward. So basically, it uses a property of the derivative of a product. So basically, you have two functions, big F, big G. You derive them in small f, small g, and then you look them up. You look them up in all the functions you know how to integrate already. And if you find small f, big G in the data set, you get big F, small g for free. So this might look like completely wonky because, it's more difficult, but we'll see why we use it. It happens because we have many examples, and you'll see that you can use it. So if you generate, you'll see why. So if you generate with forward generation, you get this kind of problems and solutions. So you tend to have short problems and long solution. If you do backward, it's the other way around. You tend to have long problem and short solution. You see forward and backward. So what you can see is that the generator here, and that was a surprise for us, we didn't think of it before, the generator explores different parts of the problem space. Everything is interesting in its own right. You want to integrate all functions in the end. But if you train on forward generated data, your model is going to see a lot of cases where you have small problems with long solution. Whereas if you train on backward generated data, it will be used to long problems with short solution. And the good thing with integration by part, and the reason why we introduced it, is that it sort of stands in the middle. We also have a backward technique for the ODE, the differential equation. You can look it up in the paper if you're interested. But basically, we ended up with 5 data sets between 20 and 40 million examples. That's what you need. In general, to train transformer, you need between 10 and 100 million examples. So we had expression with up to 15 operators, so fairly big trees. And we have 3 data sets for integration and 2 for ODE, for first and second order ODE. And the results, much to our surprise, were actually quite impressive, because if you, on integration, if you integrate and you have on the model have only one try, so there's no beam search, you're at 93, 94 to 96, 97%, even 98% performance, so accuracy. So it means that pretty much all the samples in your test set, which has not been seen at training, can be integrated. And if you use beam size, it works well. It works even better, of course, because you have several guesses. The fun thing is that this means that it's interesting because it's a very high level. It's also interesting because it doesn't depend on the generator. Since we have 3 different ways to generate, maybe the results would have been different depending on the generator. Maybe the good results might be the result of the generator, but this is not the case here. Everything has the same effect. If you go to
how would you check for unique representation of a solution? You have a
so there's no unique representation here because everywhere there's an integration constant. So I'm giving only one solution to the model.
Yes.
But at test time, any solution that verifies, the fact that if you derive the primitive, you get the derivative,
okay,
is considered correct.
Okay.
So basically, you put it into SimPy and you derive and you simplify. That's the way you check.
Okay.
For ODE, you introduce the solution into the equation and you try to simplify. If it simplifies to 0, good. If it doesn't, so you might have a few false negative this way, but very few. The SimPy is generally good, but that's the way you check it. So for ODE, what you can see is that the problem is harder, so the results are lower, but still they're totally non-trivial. Even at order 2, with just one try, we can solve almost half of the ODE in our data set. And as soon as you use beam size, it works very well. But to compare, we compared it with state of the art. So basically, we compared it with computer algebra. So Mathematica, MATLAB, Maple. Mathematica is the best on those tasks. So we mostly focus on Mathematica. And you can see, so we're sort of cheating here because we decided on the test set, etc. So we're on our turf. But you can see that we're at close to 100% for integration, whereas Mathematica is more like 85, 86%. There's a timeout. If you remove the timeout, it's around 87. For ODE, we're sort of equivalent for order 1, and Mathematica is even better than us if we have only one chance. But if we have several tries, we beat Mathematica every time. So I wouldn't say we beat Mathematica. That's not really the serious thing to say. It's more important to say that basically we're state of the art with just language trained models, knowing no math. We can reach state of the art on those relatively difficult tasks. So yay. So having done that, I'd like to point a couple of limitations of this that we had noticed at this time. So the model here is trained from generated data, and we test it on data that the model hasn't seen at train time. But the training and the test set come from the same generator, and this wouldn't happen in practice. So what if they don't? What if the test set doesn't come from the same generator? So we can naively train because we have the forward and backward and integration by part sample. So here you can see the lines are the training data and the columns are the test data. So if I look at the first line, I train on forward and test on forward, it's very good. If I test on backwards, it's bad. I mean, I'm at 11%, and even with the beam, I'm at 17%. So it's still non-trivial. I mean, the model doesn't lose everything. It still can integrate like 15% of the things I'm throwing at it, even though they are totally different, but it's not that good. If you go from backward, train on backward, test on forward, you might note that it's not symmetrical. We'll see that again, but you get like 20% or 27%. So it's not very impressive. So what's happening? So what's happening, we've seen the problem. Basically, suppose you train on the forward data. The model is going to see 40 million examples of this. It's going to see, functions and integral and learn from this. And the model only sees data. You remember, it doesn't know anything about integration or mathematics. So the model will quickly learn something, the cardinal law of integration, which is it's an exponential. You have a small problem and a long solution. And the model is absolutely sure about that because it's seen it every time in every single function it's seen during train time, or almost all of them. So of course, if you arrive at test time with this, what do you think happens? Well, it doesn't work. It's a catastrophe. And it's normal, and it would happen with different models. And, suppose you train a model to recognize pictures of cats and dogs. And if all your pictures of dogs are big dogs, and then at test time, you arrive with a picture of, a Yorkshire or a poodle dog in the arms of someone, I'm ready to bet that the poodle dog is classified as a cat, because small dogs were never seen at training. So it's not really the problem of the model, but you see the problem here. And fortunately, we have the integration by parts test sets. Actually, we designed it for this. And if you look at the first line and the third column here, you can see that if you train on forward, test on backward, it's bad, but test on integration by part, it's almost as good as forward. It's 85, 86%, up to 89%. So what you can see here is that it's not about the model not being able to generalize. It's about the model having difficulty to generalize when the training and test sets are too different from each other, which suggests that if you want to train models that can generalize very far, the way you want to do is to enforce diversity. You want to have several generators. You would like to mix and match different generators. And you can see that on the third line, if you train on backward and integration by part and test on forward, you can see that you're almost double or a little more than double the results that you had if you train just on backward. You see the impact of diversity here. Okay, so that was our first paper. And the takeaways is, okay, transformer can solve symbolic problems. They can be trained just from examples. They don't do everything right. You can see that out of distribution generalization is a hard problem and it's an issue. And you can also see that data generators somehow are key, and we want probably diversity in the data sets. So I'm going to show rapidly a second set of examples of problems. So that was a follow-up paper with, again, Guillaume Lample and Amaury Hayat, who's a mathematician. And we were focusing this time on differential systems, so system of n first-order differential equation in many variables. So this corresponds to dynamics. So these are dynamical systems, as you see pretty much everywhere in science. You get them in physics, chemistry, economics, biology, everywhere. Most of the time, these systems have no analytical solution. So the previous method won't work because there's no solution. But you can guess the properties of the solution near critical points, so near the places where the gradient is zero, so potential minima or maxima. And you can know them from theory. So we're going to try to teach the theory to a transformer and use, specifically, we're going to teach it something called the spectral mapping theorem, which is if you have such a system and you compute a Jacobian, which is a matrix of all the partial derivatives for all the variables in the system, and you evaluate it in a critical point, a point where the derivative is zero, then you have a matrix, and then you compute the eigenvalues of the matrix, which are complex numbers, and you look for their real parts. And the spectral mapping theorem says that if the real parts are all negative, then the equilibrium is stable, and the largest real parts correspond to the speed of convergence of the solution. So the thing I'm I'm wanting to do on an example, I'm starting with a system. I took a small one. Basically, we'll have system with many more equations just after a while. But start with the system. You want to differentiate the functions. So that's a symbolic operation, easier than the previous one. Then you're going to evaluate it in a point, so compute. Then you're going to calculate eigenvalues and take the largest. And on this, we want to train transformers. So you see, compared to the previous problem, this is a problem that is sort of simpler. So it's made of simpler steps, but there are a lot more steps. And there's a mixture of symbolic and numerical steps. And amusingly, if you train transformer, they work very well. Basically, if you look at the last line, you can see on a mixture of elements, from degree 2, systems from degree 2 to degree 6, so 2 to 6 variables, you basically can predict the convergence, or the largest real part of the eigenvalues of the Jacobian, within 10%, which is a relatively fair prediction level, with up to 87% accuracy, which is a lot. It's a lot for degree 2, it's less for degree 6, naturally, but it means that you can get very high accuracy on those kind of problems. So we try to up the ante and make things more difficult for the machine. So we now look for a similar problem, which is called controllability. So basically, you consider the system is over-parameterized. So you add a few variables in, which are control variable. And you want to check whether you are able to select values of the control variable, U, so that you can force the system to go from one place to another in a certain amount of time. So basically, that's important. That's how you land a module on the moon. That's how you control a satellite. That's how you control a self-driving vehicle. And this is done thanks to a relatively recent theory, which is Kalman. Basically, you have a condition. You have this time 2 Jacobians, a Jacobian with corresponding to internal variable, and the second one for the control variable. And you compute a matrix from those Jacobian. And if the rank of this matrix is full, then the system is controllable. Practically, what we want to do here, I'm starting from a system. I want to differentiate twice, with respect to X, with respect to Y. I'm evaluating. Then I'm computing a matrix, and then I'm computing the rank. And again, my transformer achieved incredible results on this. I'm at 97% at the best, more than 95%. So I got 50-50 controllable, non-controllable system, and I end up at 97% accuracy. What's even stranger is that if you look at the top left value in this table, I have transformer which have only 1 layer and 64 dimensions. This is ridiculous. This is 300,000 parameters. So you wouldn't be able to use this to do language. You couldn't classify words with that. It's not a transformer. It's something very small, and it still achieves 81%. So the puzzle here is that you remember we've seen that very simple problems like multiplication can be done with neural nets, but this very complex problem can be solved with a very, very simple transformer. And yeah, that's
and when it makes mistakes, does it make big mistakes or small mistakes? Or we don't know.
So on this problem, we don't know, but I'll have intuition on later problems on that. So let me show you. So we try to go overboard. And so that's the next step, the final boss, if you like. Basically, once you want to control the system, you want to find a matrix that allows the control. So basically a matrix, a feedback matrix. If you multiply the position by this matrix, you get the control variables. So we're looking for K. There are many solutions, but the one that is taught in textbook is this huge formula. So you still have A and B. TR stands for transpose because I have T that stands for time. So I'm using, everything. You have the kitchen sink and everything here. Basically, you have matrix products, you have exponential, you have integrals, you have inversion. So it's a huge formula. And I want to train my transformer to predict the coefficient of this matrix. By predict, I mean I want the coefficients to be right up to 10%, all the coefficients within 10% of the solution. And if I do that, it starts to fail. So it doesn't fail totally. So you can see the first line in this paper, in this table says how many matrices in my test set from degree 3 to 6 can I predict with less than 10% error on every coefficient of the matrix. And you can see that for degree 3, it's a small matrix for degree 3. You got that about 50% of them can be predicted, which is totally non-trivial, but unfortunately it goes down very fast. At degree 6, you're almost at 0. And so it's not, it doesn't work very well. But you have to remember that there are many solutions to this problem and you can test them. And the system always sends you a matrix. And if you test them, you notice that actually 2/3 of the matrix predicted are correct. They're correct solution to the control problem. And there's yet another problem, which shows that, so that's part of your answer. I mean, when it fails within the 10%, most of the time, it's still a correct prediction matrix. And this, again, is very puzzling, but it sort of heavily suggests that some of the mathematics are understood here.
And when you say you test them, what do you do exactly? And
basically, you re-input them into the system. So there's the full formula is in the paper. You can, you can re-input it and compute something with the Jacobian to prove that it's solved the control problem.
Oh, okay. But what is this? What that step is not included into the learning? That No. But you could do it. You could have a. Could you do that step of testing that?
Yeah, but then you would have a precision on the testing step, so it would have to be a different transformer to do that.
Okay.
So it's, and then you have an approximate testing. So how do you judge the validity of your training? It complicates.
I mean, you test again at the end, but at least you have an extra.
Yeah, you could do that. Yeah, definitely. So the takeaway here is that you can have transformer learn very complex algorithm that features symbolic and numerical steps. We can use them not only to do symbolic math, but also to do a mixture of symbolic and numerical math. We can sometimes work with very small transformer that wouldn't be fit for language tasks. And some of the math seem to be understood. So I'd like to present a third paper, which is a recent one, which is something I did last year. So basically, it was about only numerical computation. Math is not only symbolic manipulation. I want to do numerical. So basically, could we do linear algebra? So I studied 9 problems, basic matrix operation, and more difficult things like eigenvalues, eigenvectors, singular value decomposition, matrix inversion. So basically, we work from dense matrices, coefficients are rounded to 3 digits, etc., and encoded on 3 token, sign, anti-sign exponent. Not really important. So the main takeaway here is that basically algebra is learned with very small models. Usually 1 or 2 layers are enough to learn transposition, addition, multiplication, all that. You can also learn eigenvalues and eigenvectors and SVD and matrix inversions with more than 90% accuracy. So it's not, don't do this at home, it doesn't replace NumPy, but it's interesting because it's not very clear how transformer learn that, because these are very nonlinear and strange, they're difficult calculations. So I'd like to just focus here on one aspect. So when you compute eigenvalues, what you notice is that there's a scaling law. So if you learn with 6-1, so transform with 6 layers in the encoder, 1 layer in the decoder, you can learn it with 40 million examples. You can learn the eigenvalues of 5x5 matrices. With 60 million examples, you can learn the eigenvalues 8x8. And if you scale the model to 12 layers, 24 layers, so that's BERT basically, you could achieve 12x12 matrices. And the funny thing is that the larger the model, the less examples you need, which is counterintuitive. I thought I would say that here. That's something we observe. But I was interested by this problem for another reason, because you remember my problem with out of distribution results, and this is a place where I could test it and study it. So here, when computing eigenvalues, my models are tested on symmetric matrices with independent coefficients. And these correspond to a class of matrices, which are very common in physics, notably, which are known Wigner matrices. And we know that their eigenvalues are distributed around a very fixed law, which is a semicircle law. So eigenvalues are, half of them are positive, half of them are negative. Their variance depends on coefficient variance and matrix dimension. The support of the eigenvalues is bounded. So the question is, okay, suppose we train on this, could we generalize to different matrices, to non-Wigner matrices, to positive matrices, for instance? And so I'm generating new eigenvalues distribution. Okay, there's a trick for that. It's not really important. You can look at it if you're interested. But I'm considering 6 new eigenvalue distributions. So symmetrical distribution, so with Laplace, Gaussian, uniform distribution of eigenvalue, not semicircle. And then positive matrices, so matrices which have only positive eigenvalues, which are very different from the symmetric eigenvalues. So we are very far apart, like my forward and backward before. And Marcheco-Pasteur, which is the distribution of eigenvalues of covariance matrix. So these are statistical matrices, if you like. So that's the closest I could think of something that would look like a real-life distribution. And this is the kind of thing you find in statistics. So it's the same table as before. You have 7 training sets and 7 test sets. Training sets are in line, test sets are in columns. So let's look at the first line. So if I train on my Wigner matrices, so semicircle eigenvalues, you can see that I get 100% on semicircle. That's what I told you. But as soon as I get out of distribution, things fall apart. So if I'm on symmetric, I'm at 34, 36, 39 for uniform Gaussian Laplace. So it's not very good. And if I try with those symmetric eigenvalues to predict positive matrices, it fails. I'm at almost 0%. So it doesn't work. And if I train on positive matrices, of course, I cannot predict anything like semicircle or uniform Gaussian Laplace. This is normal. I mean, the model has never seen a negative eigenvalue at train time. It's not going to invent one at test time. It's impossible. But the funny thing are line 3 and 4. You can see the Gaussian and Laplace distribution, which are weird distribution. This is not the kind of thing you would think of naturally, because they are matrices where the coefficients are not independent. So it's not the kind of matrices that appears naturally in life, in science, or anywhere. But on those specific distribution, you can see that not only can they generalize to 100%, so they work, but they can generalize to semicircles, to Wigner matrices, whereas the opposite doesn't exist. And they can even generalize to Marchenko, to positive definite matrices, even though there are almost no positive definite matrices in the train sets. So this suggests, on this very specific case, that out-of-distribution generalization is actually possible if you carefully select the training distribution. How to select it is, a problem that still needs to be studied. And a fun fact about that is that those robust distributions, so the uniform Gaussian, the Gaussian and Laplace mostly, they are not only good at generalization, they also train faster. So here I try to train on only 36 million examples. That's not enough to discover the eigenvalues of 88 matrices normally for semicircle matrices. But you can see if I train Gaussian and Laplace, not only do they compute Gaussian and Laplace eigenvalues perfectly, but they also compute Wigner eigenvalues and positive definite matrices eigenvalues with 100% accuracy, with less example that would be needed. So if you want to predict Wigner matrices, your best bet is a Laplace matrix training set, because it will generalize and it will train faster and it will train to larger matrices. So the takeaways here is that, okay, you can learn computation. It's not only symbolic math, you can also do numerical math with transformer. It works too. But the more important result is that out-of-distribution generalization is sometimes possible. And to my knowledge, the first result that shows this. You have special robust distribution that seem to exist that allow for this, and they also allow for faster training. And I'm beginning to have results that suggest that they might be problem independent. So Laplace matrices seem to work for eigenvalues, but also for eigenvectors and to some extent for matrix inversion. Okay, so those are my main results. I'd like to finish by showing you a few other results, which is a side question, but it's at this point you see, okay, I hope I've convinced you that transformer can learn some mathematics, but there's a deep question here. Do we really learn the math? Or are we just, parroting? Are we just learning shortcuts? It's been said that large language models are stochastic parrots. Are we just exploiting statistical patterns? Also, you asked about the failures. Yeah, what about the failures? Are they really predictable, principal, or as in NLP, are we hallucinating models? And finally, there's that nagging question, why are easy problems, some easy problems so hard to learn and hard problems very easy to learn? So I'd like to show 2 examples, one case where the machine will learn the math and one where it won't learn the math. So the first one is the greatest common divisors. So I'm trying to learn the greatest common divisor of 2 integers. And this is current work. So I'm generating pairs of random integers between 1 and 1,000,000. I'm computing the GCD and I'm training a model to predict it. And I'm testing on a held up data set of 100,000 samples. The problem size is huge, 10 to the 12th, so the model is not going to memorize or learn anything, by heart. And I'm trying that. So my first experiment, I'm encoding my input and output. They're integers. I can encode them in any base. So I'm using base 30, large base, so that the representations are smaller, and composite, so that sort of helps the model, I've noticed. I'm using my very small transformer, unfit for language, 1 layer, 64 dimension. And the fun thing is that, I get 85% accuracy after one epoch. Only 300,000 examples are enough for the model to predict the correct GCD in 85% of the cases. And if I use 45 million of examples, you can see that the curve saturates, but I'm at 95% accuracy. So looks like the math have been learned there. Or have they? Because if I repeat the problem, instead of encoding in base 30, I'm now encoding in base 31, prime number. And you can see the result is the green curve, green and yellow curve at the bottom. That's accuracy, 61%, but it plateaus at 61%. It looks like accuracy is base dependent, and this shouldn't be the case. GCD doesn't depend on the representation. It's a pure mathematical thing. And actually, if you try more base, you get that graph. So top to bottom, you get base 30 and 6 and 10 and 2 and 3 and 31. Yeah, what the hell? You get different results for different bases. Are we really learning the math? So at that point, you want to have a look at what the model is actually predicting. So a little theory, the probability that the GCD is K is proportional to the inverse of the square of K. That's an old theorem from Cesaro. And so it says that 61% of my random pairs have GCD1. You remember the 61, which was the value on 31? That's where it comes from. Basically, the model has guessed very fast that 61% of the case, if you reply 1 to the GCD, you get 61%. So when in doubt, it predicts 1. But what's more interesting is that you notice that the model, when you look at the result, the model only knows the GCDs that are products of prime factors of the base. So for instance, in base 2, GCD 1, 2, 4, 8, 16s are correctly predicted all the time, 100%. The rest is perfectly wrong. Actually, for the rest, the model seems to be counting the rightmost zeros. So for instance, if I want the GCD of 28 and 14, should be 14, in base 2, they're written 11100 and 1110, and the model is going to count the zeros. Note that there's 1 0 common at the right and answer 2, and it does. Sometimes it's right. If you try 68 and 64, this wrong method will work. So it's like a bad student that has developed a bad way of computing something, which sometimes happens. But you can see that here, the math have not been learned at all. And you can understand my results because in base 30, which is 2 times 3 times 5, GCD 1, 2, 3, 4, 5, 6, not 7, 8, 9, 10, not 11, 12, not 13, not 14, are learned perfectly. So that's where the 95% come from. In base 31, you only get 1 and 31, so that's where the 61% come from. So the model is cheating, and it's exploiting representation to compute the easy case while steadily failing on all others, and the maths are not learned. So here you have a case where the math are not learned at all, and new techniques are needed. This is current research at this point. New techniques are needed for the model to learn the GCD. There are cases where the math are learned, and this seems very clear. This is my last example. So I'm back with my matrices. I'm trying to teach them to diagonalize, so to compute eigenvalues and eigenvectors. Specifically, I'm giving the model a symmetric matrix M, and I want the model to find a vector D and a matrix H, verifying such that H is enough to transforming by H, transform matrix M into the diagonal D. So that's diagonalization. The model is going to learn this only from examples, but we know theory. We have learned that this is a spectral theorem, and we know from theory, but the model doesn't know it, that D are basically unique, that the eigenvalues, they're only one set, up to a permutation, up to an ordering. And that H is an orthogonal matrix, unitary matrix, which means that the rows and columns of H must be orthogonal 2 by 2 and have unit norms. So what I'm trying to do is say, okay, suppose I train the model to learn to predict D and H from M. We've seen that we can do this with good accuracy. Are we going to learn those theoretical properties and what does it mean to learn them. So to this effect, what I'm doing is that I'm training my model to high accuracy, 92 accuracy here, and testing it on 100,000 matrices not seen at training. So I'm going to get 92,000 correct predictions, good for them, and 8,000 errors, which is what I'm interested in. What I observe is that in all my test cases, so all the correct prediction, of course, but also all the errors but 6, so that's 99.99%, eigenvalues are predicted correctly with less than 1% error. Even when the model is wrong, the eigenvalues are right. And in almost 99% of test case, all rows and columns of H have unit norms. So those two properties of diagonalization are respected even when the model fails, which answers your previous question on how does the model fail. But interestingly, what I think is that that's a good proof of that some math have been learned. You know, if you have a student that consistently respects some property, even when he fails the rest of the calculation, you can consider the properties has been learned. Same here. It's even more interesting because if you could be in a situation where the model learns to predict and at the end he learns the theory, but that's not the case. If you only half train a model, so you train it for less time to 70% accuracy. Well, even on a half trained model, the eigenvalues are correct in almost 100% of the case, and the rows of columns of H have unit norm in 97% of the case. If I go to larger problem, and on those larger problem, my model only achieves 43% accuracy because I would need a larger model. I don't have enough capacity in the model to learn. Yet the eigenvalues are correct, and the rows and columns still have unit norm. So what's fascinating here is that the math are learned, but also that the model doesn't hallucinate. When it's wrong, it remains roughly right.
But do you think that the model could state the spectral theorem?
I have absolutely no idea on how I would output that as language.
Interesting, right? You say so. You will invent new theories, a new theorem, right? Like you say.
That would be fascinating. That would certainly be fascinating. Yes. So I'm almost finished. That two before last. The funny thing here is that we understand the model failures. We can see that all the model failures can be attributed to one single cause, which are the rows and columns of H not being quite orthogonal. They're almost, but they're not quite. And we can even design a technique to predict the failures. In that case, if you look at the condition number of H, so the ratio of the largest to smallest singular values of the matrix, it should be 1 if the matrix is orthogonal. If I look at it, if it's slightly larger than 1.0445 worked for me, I can predict 99.3% of model outcomes. So I know just by looking at the prediction if the model is right or wrong, by looking at the number, and it will be right almost all of the success and 97% of the failures. And the funny thing is that this works also for another problem, a famous problem, which is matrix inversion. So in that case, I have a matrix. I want to predict P such that MP is close to identity. My matrices are invertible, so M-1 always exists. The inverse always exists. All my models, no matter the size, struggle to achieve more than 90% accuracy. I've noticed that. The thing is that they predict something close to the inverse, but it's not a good inverse. I don't have MP close to identity. And this is because of a mathematical property which is taught in classes. If you learned about matrices, you remember about this one. It's called ill conditioning. The matrices are ill conditioned. And it's a typical, NumPy will fail on that. Humans will fail on that. And actually, the condition number of M, if you look at the condition, if the condition is large, if the matrix is in condition, 98% of the model outcomes can be predicted this way. So you don't even need to run the model. The model fails if the matrix is badly conditioned. What I'm stating here is that the model is failing for a very good mathematical reason, the only good mathematical reason there is for failure at matrix inversions. So again, in this case, this is not the case for GPT-3, but this is the case here. Failures are totally principal and they're totally predictable in this case. Okay, so I think this was pretty much my last slide. So basically the takeaway from this is that transformer can learn math. And it's sort of a new field of research, and it has application for science. So if any of you is interested, please ping me. I'm interested. And we learned also something else, which is that it's possible to use mathematical tasks to help understand deep learning and transformers. So we can also use math as a tool for transformer explainability. So yeah, that's all I had to say. Thank you very much.
Thank you very much, François. That's fascinating. Okay, so we can open it up to questions. So please raise your hand on the thing, and we'll let you ask the questions. While you're thinking about questions, you can ask François. I'm thinking of, so if people want to do that like at home or like on their, is it possible to do it on like without having access to Meta, like cloud computers and so on?
Yes, yes. The fun thing is that this is much easier to run. Actually, there was a moment when I did that when I was not working in Meta, and I did it on an a gamer's machine.
Oh, okay.
So basically, so for the easy problem, you need like 6-layer transformer, 6-1 or something like that for the linear algebra, for instance. So if you have a machine, the problem will be the GPU memory. But if you have a machine with like 16 GB of memory or 10 GB of memory, you can probably run models on this.
Oh, okay.
So you could run this on gamers' machines or stuff like that. You don't need a cluster.
Yeah.
Where the cluster is a big help, where having hundreds of GPU is a big help, is transformers have a lot of parameters, of hyperparameters. And if you want to get, very good results, you need to sweep. And if you sweep one GPU at a time, one experiment at a time, you're going to need a lot of time. But we're not in the realm of large language model. I mean, the largest model we have here have, 50 million parameters or something like that. So they're by no means comparable even to, we're not even at BERT small. We're smaller than BERT.
Okay, yeah, excellent. Even now, people have access to cloud computing quite cheaply, so they can have access to GPUs and so on. So it's really...
the computing time might be, if you pay for your compute, the computing time might be something, because on some problem you need a week of compute or something like that to solve one problem.
Okay. Yeah.
So yeah.
Okay. Any questions for François? Maybe they need time to digest. I think if you Google François Charton, his Google Scholar page, I think you have many of these papers.
I think most of the paper are AI for math. So
no problem. Archive and so on. So do you have collaboration with other scientists, or like people who are like interested in applying exploring other kind of math, like physicists or
there's a number of
people
I haven't presented them here because there's a number of collaboration with fair colleagues or PhD students and all that. But I have a couple of collaboration with actual scientists, people who do science, not just AI.
Yeah.
And so, for instance, I'm collaborating right now with a team from FAIR who's doing cryptography. So we're using Transformer to try to do cryptanalysis of post-quantum cryptography. So basically, this is modular mathematics.
Yeah.
So math on lattices. So we're working on that. I also have a collaboration with physicists, with theoretical physicists from SLAC, the Stanford Linear Accelerator. We're trying to infer the properties of something called the scattering amplitude of gluons. So properties of some low-level particles. And so this is basically using the same kind of techniques, but in order to do math that are, useful for physicists or mathematicians. So this is the kind of direction I'm exploring right now.
Okay, that's fascinating. Okay, so last chance. Anyone wants to ask any questions? I mean, you can find François' contact page on LinkedIn. So thank you very much for your time. I think I hope it will inspire like many of us to do research or to explore this area. So another frontier, I think, goes beyond ChatGPT and so on. So I think the world of AI is like very rich. I really believe it's like it's really the scale of a new industrial revolution, I think, for science. So thank you very much, and please keep in touch. And next month we'll have a speaker who'll talk about satellite imaging. So it'll be different topics, but what the state of the art in AI and satellite imaging. So thank you very much, and have a great rest of your day. Okay, thank you, François. Thank you. Bye-bye. Bye-bye, everyone.